So there's one other way for you to approximate the area, the definite integral, and it's with something called Simpson's rule. Okay. And this is another method for approximating a definite integral. And I'll give you the formula in just a second, but what I want to tell you is, okay, with Riemann sums, how did we approximate the area? What objects did we use? We used rectangles, or if we did the trapezoidal rule, we did trapezoids, right? So the tops of those things are made up of straight lines, right? The top of a rectangle is a straight line. The top of a trapezoid, it's part of a line segment, right? Part of a line. So, but in general, curves are not very straight, right? Curves go up and down and all around, right? So, we want to account for that curve. So we're going to use a different object, something that has a curve in it. A parabola has a curve, right? So the idea is that use parabolas to approximate curves. Okay? And I don't really want to get into all the messy details of this. I think your book has a proof of the formula that I'm about to give you. So if you want to look at that, you can. But what it says is that the integral from a to b of my function is approximately this s sub n that you get from Simpson's rule. And what s sub n is, you take delta x and divide by 3. And this formula looks kind of similar to the trapezoidal rule, but the coefficients are different. So my coefficient of x naught, my beginning is 1 still. And then after that, my coefficients are going to alternate between 4 and 2. F of x n minus 2 plus another 4, f of x n minus 1. And then my last one, the end of my interval, the coefficient goes back to 1. So it's kind of in the same spirit as the formula for the trapezoidal rule, but it's a little bit different. And because of the way that the formula is written, we have to have n be even in order to do this, okay? So where n is even.
Is that a 4f to the x3?
For where?
It's
the first line?
Second line.
Second line, that's 4f x3, yes. Yeah. Are you gonna let me erase it? Yeah, that's a x3. All the odd indices are getting a coefficient of 4. The even ones are getting a coefficient of 2, with the exception of the first and the last, which have coefficient 1. Okay? Any questions so far?
Which one would this apply to? Just in general?
You can use this on anyone, just like you can use a Riemann sum, but with Riemann sums, you can choose the number of rectangles you have to be anything. You can choose it to be 3 or 5 or whatever. Here, you have to have an even number.
Would you recommend using this one?
This one is it depends on your function. Like if my function is a straight line, then a Riemann sum does a pretty good job of it does a really good job of approximating it. But if I have a function that's very like curved, then this does a better job because it's accounting for the curvature that's going on because I'm using parabolas.
Alright.
Yeah. So I think in general, this might be better than just a regular Riemann sum. Any other questions? Okay, so let's do, since we have time, I think we got time, let's go ahead and do a problem with Simpson's rule.
Is that what that one's called?
That one's called Simpson's rule. Yeah. It's probably named after some mathematician with the last name Simpson, would be my guess.
Mr. Jackson knows.
Yeah, probably. He knows all the history much better than I do.
Gets me every time.
I at least know how to pronounce some of the names, so that's pretty good. Okay, so let's say we want to use Simpson's rule with n equals 10. Again, I have to choose n to be even to approximate the same integral we've been talking about this whole time, 1 to 2 of 1 over x. Okay. Okay, so just like with Riemann sums, you start by calculating your delta x, because you need that for the formula. Delta x, right, it's b minus a over n, 2 minus 1 over 10, so 1/10 or 0.1. Okay, and my function that I've been integrating is 1 over x. So we're ready to use our formula for Simpson's rule. So the formula says S10. I take delta x, which was 0.1, and I divide by 3. And to that, I'm going to multiply the following sum. So I start with f of 1, and then you're going to keep adding delta x. So I would get f of 1.1. My first coefficient is a 4. Remember, they alternate between 4 and 2. 2, f of what would be next? 1.2. Okay. 4, f of 1.3. 2, f of 1.4.
So let's go all the way up. All the way up.
All the way up until you get to 2, and then you have to remember on 2, you no longer have a coefficient. It's just a coefficient of 1 now. Okay, so you keep going. Plus, 4, f of 1.5, plus 2, f of 1.6, plus 4, f of 1.7, plus 2, f of 1.8, plus 4, f of 1.9, and now I'm finally at the end, f of 2, and you don't have a coefficient for that guy, okay? So it's not very nice. You plug all this into a calculator to tell you that this is approximately 0.693150. And you can compare this with the trapezoidal rule. You'll see that the number's a little bit different. Let me look back. Our trapezoidal rule gave us 0.691908. Okay? So this estimate, it's a little bit different, and actually I think it's a little bit better than the one we had with the trapezoidal rule. Okay? All right, so I want to end, I think, here.